This talk is about quantum network protocols and how to quantify their behavior. Quantum networks are networks connecting quantum-capable devices. Now, all the talks in this session are interested in what's happening inside individual quantum devices. And we want to connect these devices together and make them communicate with each other. Each device in the network has a few of so-called communication qubits, designated to establish connections with other devices in the network. By being connected, we mean that distributed devices can share entanglement. Quantum networks bring benefits. For example, scaling of quantum computation, that it's also part of IBM Quantum Roadmap. Another benefit is that they enable secure communication with killer apps such as teleportation and entanglement-based quantum key distribution. Quantum networks are indeed becoming a reality. With test beds emerging across the world and entering practice, computer science is here to drive further advances in this area, and in this spirit we are here. Bell pair is the fundamental entanglement resource in quantum networks. Bell pair is just a pair of entangled qubits. This is a Bell pair model here at Art Science Museum in Singapore. We denote a Bell pair by a tilde connecting the nodes that contain the entangled qubits. Now, but one limitation of Bell pairs is that they carry no control information. Thus, quantum networks need to be built on top of classical ones. Classical networks consist of end nodes that are connected through switches via classical channels. On top of this, quantum networks have separate quantum channels, quantum-capable end nodes, and repeaters to overcome large distances. Some of these nodes can also act as quantum sources where Bell pairs are created locally. Now let's have a look how protocols run on such architectures. For simplicity, I will present network's topology as a graph. In a classical network, a packet, which is the information carrier, is forwarded through switches from source to destination, hop by hop, 1 and 2. Below, we record the path that the packet has traveled. In quantum networks, however, qubits cannot be forwarded over large distances due to their decoherence and the no-cloning theorem. Now, let's describe our running protocol example that generates an end-to-end Bell pair between nodes A and B. The protocol runs in 3 rounds. In round 1, we create 2 Bell pairs locally at C. Below, I will write the execution traces that record the multi-set of Bell pairs in each round. In round 2, we transmit 1 qubit of each pair to the neighbors, A and B. And in round 3, we perform so-called entanglement swapping. This action is Bell's measurement at C that exchanges the 2 Bell pairs into 1 over larger distance. This way, we generated Bell pair AB. Now, given that quantum networks work like this, we need to make sure that they behave as intended. With our previous work, we were able to address questions like, does a protocol establish Bell pairs between the specified nodes? Are 2 protocols equivalent? Or can protocols run in parallel? And as a solution, we provided a foundation to answer these types of questions, which by designing the PBKAT language that we presented at PLDI last year. With the work I'm presenting today, we want to reason about quantitative properties of such protocols. And we want to answer questions, what are the probabilities at which our protocol produces AB? What is the expected number of protocol iterations? Or can we improve the rate at which Bell pairs are generated? And again, as a solution, we provide formalism to answer such questions by designing a language for quantifying quantum network protocols. The name PBKAT stands for probabilistic bell cat, that alludes to bell pairs and Kleene algebra with tests cat. PBKAT's key feature is that it captures probabilistic behavior for expressing failures and combines it with non-deterministic behavior that arises from concurrency. In what follows, I will introduce the language components through our running example. So in round 1, we create 2 CCs locally. In round 2, we concurrently transmit them to A and B. And in round 3, we swap them. The indices indicate the success probabilities of each action. And above, we will write the execution traces and assume that at the start we have no bell pairs. So in round 1, we create 2 CCs locally with probability 0.81. But we may only succeed in creating 1 or none. If 2 CCs were created in round 1, in round 2, we transmitted them to AC and BC. But again, we might have only succeeded in transmitting 1 or none. The case where only 1 CC was created in round 1 becomes more interesting. Let's say that there is a scheduler that non-deterministically transmits CC to either AC or to BC. And the remaining case where no CCs were available after first round, there is nothing to transmit. And finally, in round 3, the swap action can only attempt if it has both AC and BC available and succeeds with probability 0.6. And in all the remaining cases, if the swap doesn't get the required bell pairs, so nothing happens. At the end, we combine, collect these traces into protocol output. How? The probability of each output multiset is obtained by compounding the probabilities along the paths that lead to it. So for example, we output the, is the cursor? Okay. We output the empty multiset with probability 0.29 by compounding, by summing up the paths here, along the black parts and the brown one. Thus, the probability distributions mu and mu prime come from non-deterministic choice. Finally, we present the output as a convex set of probability distributions. Why? Intuitively, each distribution in these convex sets corresponds to a different strategy of the scheduler. For example, if the scheduler prioritizes transmitting to AC, then we get this distribution. Or if the scheduler randomly transmits CC to AC or BC, then the output distribution is here in the middle. As you've just seen, we write protocol PBKAT protocols as expressions that consist of basic actions such as transmit and swap, guards that test for available bell pairs, together with constants for skip and abort, and we combine them with conditionals, sequential composition for transitioning through rounds, and while loops. We also have parallel composition and ordered composition that is a variant of parallel composition, where E always has priority over F when grabbing bell pairs. PBKAT semantics is built in 2 steps. First, the abstract semantics interprets the PBKAT expression as a guarded strings of sets of actions. And then the execution semantics produces the output which is convex set of distributions like we saw in the example. We also implemented a tool that enables writing PBKAT expressions in an embedded DSL inside Haskell. Here is a snippet. So F first creates CC locally, and then it conditionally transmits it. And below, F is in parallel combined with some other protocol E. So from an expression, the tool builds an automaton that captures the abstract semantics, and then it computes the execution traces, and it outputs the convex set of distributions. To summarize, we designed PBKAT language for expressing real-world quantum network protocols. We prove soundness of its axioms with the semantics that enables protocol verification and optimization, and we built a prototype tool for quantitative analysis that we evaluated on 16 protocols that all took under 10 minutes to verify and used at most 8 gigabytes of memory. And with this, I thank you for your attention.
Thank you.
I have two questions. One is, when you have a probability of failure when transmitting, is that completely, I guess, classical, or is it like, I think of that as there's like some fidelity of the state I actually transmitted, or is it completely like?
So yes, it's classical in the sense that you treat the actions or operations as the black box, and actually the early generation schemes or protocols are going to be implemented so that you will get a heralding signal, which is a classical signal that will acknowledge the success or failure of your action. So you will know what you succeeded with.
I see. Cool. And my second question is, I don't know that much about quantum networks.
Yeah.
So are bell pairs like the only, I guess, primitive that we need in them? Or does this generalize to other types of entanglement?
So bell pairs are the resources of quantum networks, and you use them to run applications on top of them, right? Like teleportation, and each of these applications, to transmit the information with teleportation, for example, you will burn the bell pair. The same with, or you will use it to transmit. And yeah, so that's the work. Of course, there are many multipartite entanglements which are less stable. So the benefit of this is that they are maximal entangled bell pairs. So they are the strongly correlated as you can possibly find. So they are and easy to produce.
Oh, cool. Thank you.
Could the next speaker come up and set up? But I have one more question for you. What's the largest example that you tried your new technique on?
So the examples are small, of course, because you have XP complete. Like
yeah, we just move your computer.
We just generate all the traces.
Yeah.
But the complexity actually doesn't come from the size of the topology, but from these nested for loops.
Aha.
Okay. So that's why. So the examples that we have are like on 5 nodes and chains.
Okay. And that's already quite a challenge.
Yes,
okay.
yes.
Very good. Thank you again.